So last time we solved this problem, which is of finding your route in a maze. Okay, so you are given a grid with obstacles and you have to find a path from S to T, shortest path. And this has a very clever implementation using a queue. Any questions about that? And then we went back to balanced binary search tree. And in these last two classes, we will finish the implementation of red-black tree. Okay, so for AVL tree, I have given you only one idea, which is that of rotation. When you insert or delete, then to balance, you have to rotate. That we will now explore in detail in the case of red-black tree. So first we define what this is. So the definition will be strange at first. Because historically these were not discovered first. First you had more intuitive kind of trees. So red-black tree is a binary search tree such that each node is colored either red, which for this course I will denote red by a circle, or black, which for drawing the tree I will use square box. Okay, so every node is either a circle or a square. So it is either red or black. Each leaf is mandated to be black. So let's just continue with this color. So each leaf will be a square. And in fact, leaves will be forced to have the null pointer. Okay, so each leaf will be empty. It will not store any node. It will not store any record or key. So leaves are special. So that is about the colors of the nodes. Then there are two conditions on how these colors will behave with each other. So each red node has only black children. Okay, so which means that a red node can have two null pointers, which will be leaves. So they are by definition they are black, or they may have one of these or both of these children to be records, but then those records have to be, nodes have to be black. Red cannot have red child. And the final condition is that number of black nodes on each path from the root to any leaf. So on any path from root to leaf, you want the number of black nodes to be the same. Okay, so this number is called black height. So BH of T. Okay, so this is a unique condition. Originally, a height of a tree could be different on different paths, or the length of the paths can be different. We only define the longest path as the height, but black height is very strict. Every path from root to leaf has to be of the same black height, same length. Is this clear? So this is the data structure which is called red black tree. It has tons of properties, and we'll try to pack those properties into details. So we have to go a bit fast on this. It seems very exotic, but this is the most useful tree which is applied in all these applications. In Unix also, in operating systems also, many of the data structures are actually based on this implementation. Okay, this is a very practical data structure. So the first lemma, major lemma that one proves here, shows the utility of these axioms. Or maybe I should give an example first. Yeah, any questions about this? These axioms, what do they mean? So let's draw a red black tree. So this 28 is a red node, 46 is a black, 46 and 67 are black. So 28 can have only black children, right? So 28, for example, can have 5 and 35, but then you have to color them black. And 67 is black, it can have any kind of children, so 49. And then 49 ends with leaves. So there should be a leaf here also. So till now on the right side of 46, what is the black height? Black height is 3, right? There are 3 leaves, and you can see that every leaf path from root to that leaf has 3 square nodes. No, we have not, I mean, in the axiom we did not say anything. Yeah, from root to leaf. Sorry? No, it's about it. Look at a path from root to leaf, count the number of black nodes. So here 46, 67 and the leaf, so 3. But this is not true on the left side, so which means that it's not complete. So let us give it more nodes. So let's say 2 and 25. And then we can end with leaves. And 35 is still not complete. So we can do a similar thing. 31 and 41 maybe. Okay, so these are now 4 leaves. So now you can see that in every path from the root, so this is a red black tree. Is this clear now? So all the axioms here are axioms that we stated are implemented, are being followed here. Red node has black children only. Leaves are all black and store the null pointer. And any path you go from root to leaf, you will see 3 squares. Okay, so that covers all the axioms. Any questions? Right. So yes. Yeah. It only has null pointers. Sorry? Number 2 has 2 children, both are leaves. No, it has just some books will show it nil, and we will only show it by a cross. So it doesn't store anything, it is just a black node empty. Okay, so the property that we want to show is that any red black tree has overall height at most log of the size of the tree. Okay, so this was the original promise that I mean, this is one of the promises that the tree has to have small height in terms of the number of records n. Height should only be log n, and then the other promises are, which we will see, that how to do insertion deletion in this much time, right? But as you have seen before, in a tree, in a BST, it takes height of the tree much time. So if the height can already be much bigger than log n, then it won't be of any utility. So the first important lemma is that actually that's not the case. It's a good case. Height, just those axioms that we have put, they enforce that the height cannot be more than order log n. So why do they imply this? Right, this requires a proof. Yeah, so maybe one small property you should observe. What is the connection between black height and height? Yeah, so that is the correct call. So black height is well, okay, let me have both the bounds, I think. So black height is at most the height. And what can you say about lower bound? So for the lower bound, you think of black nodes. So there can be a sequence of black nodes, successive, but can there be 2 successive red nodes? That the axiom violates, right? So for every red, there has to be a black in the neighborhood. So which means that black height will be at least height by 2. Is that clear? So your question whether this bound is for black height or height, it doesn't matter, because when height is small, black height is small, and when black height is small, then you see that the height is less than or equal to twice black height. So height is also small. Okay, so both are similar, at least asymptotically they are the same. Is that clear? So 2 reds cannot. cannot appear successively in a path. So that's basically it. So blacks in a path will always dominate. There will be one more usually. I mean at least more than red. Yes, but we have to prove the lemma. That is trickier. It's not clear why the lemma should hold. So let's see a proof of this. Let MH be the smallest red black tree. Let's call the red black tree RB sub H of height H. Exactly equal to H. Okay. So this is a similar starting point as we did before for balanced binary tree. There also we calculated in the proof the smallest size tree that balanced tree you can have for a given height. Okay, so similarly here also let RBH be the smallest in terms of size of number of nodes red black tree that you can have for height H. And let us again find out the recurrence like we did before. So we can assume without loss of generality that this RBH has its left path the longest. Okay, which means that so pictorially you have the root and then you have, let's say red is the root, then you have a black child, and then again you may have a red and so on, and then it ends in a leaf which is null. Okay, so we can assume that the tree RBH will have a longest path of length H because we have assumed that it has height H. So let us just orient ourselves and say that the leftmost path is the longest. Okay, and now the other paths to the other leaves could be length H, or they could be overall length H, or they could be smaller. And since we want to minimize the size, most of them should be smaller. Right? If you make all of them length H, you will get a complete tree which will be very big. But RBH has to be the smallest tree. So others you will save. On this path you cannot save. So yes, so this path, this longest path has how many red and black? Let's make a statement about that. So how many red nodes will there be on this path? Yes, so why is that? That is a tricky claim, right? It's not obvious. because we only know that this is the longest path in RBH, but we don't know its colors. Why can't it all be black? So the logic here is that if every node in this path was black, then this blows up the black height to max. And then to every leaf, you will have to maintain that max height. That is not a good idea. That will blow up your size, right? So you have to argue here that this path has maximum possible red nodes. Because if you miss even one, else the black height increases, and that has to be maintained for all other leaves. So which will mean larger size. Okay, so the more on this one path already, if you have many blacks, then it forces other leaves also to have the paths also to have that many number of blacks, and so you actually you have to work out this this green hint and deduce that this path actually has maximum possible red nodes, which has to be around half, right? So this means that this path has H plus 1 over 2 black nodes, and then H minus 1 over 2 red nodes. Is this clear? Or maybe opposite actually. You want less black. Yeah, so you want as many red as possible, so you can have just above H by 2, not much more, right? Or it can be equal. If H is odd, then it will be equal. There might be an issue here. I think by height I mean here number of nodes, which is slightly different from what we had defined before. So let me redefine it here. Okay, so simply for this diagram, let me just redefine H to be the number of nodes. So H plus 1, H minus 1, but let me not go into that. So number of nodes overall is H, and reds cannot be more than black, and also we want to minimize the size of the tree. So overall, red you can afford H plus 1 by 2 floor, and black the remaining, which is H minus 1 by 2 floor. Okay, so this will give us something now. This will take us towards a recurrence. So the question you have to ask here is, what is what is the remaining part? What can you say about this? So what is this part? So we have identified the longest path on the left, and we also have identified how many red and black it should have. Now, what is remaining for the recurrence is all these right children of all the nodes on this unique path, on this important path. So what can you say about that? Again, keeping in mind that you want this to be minimized in size. Yeah, perfect. So they are all black, which means that and also you have to preserve this property of h minus 1 by 2 black on every path. So you will have kind of a complete tree, right? So you put a complete tree of this much height. Yes. Yeah, don't worry about this minus and plus. You just pick something. So my notation here is I am just thinking of h nodes on this longest path. What is more important is structurally this right part is complete. It's completely black. Now, okay, maybe one line can be said about that. Of this path, all the right subtrees of this path should have only black nodes as you want to minimize the size. Basically just this one reason. Okay, so since we want to minimize the number of nodes, actually I think there is one more reason. Let me write that also. We want to minimize the number of nodes, and second point is that all paths to leaves have length have a black height equal to h minus 1 by 2. So since every path from root to leaf has to be of this length, and since you want to minimize the number of nodes, the only solution is that you only pick blacks and these many. Yes? Sorry? It should be what? It should be at least h by 2. Yeah, so this is again the minor, well, okay. So then this question will keep appearing. You guys will keep asking it. So let us correct everything. So this height is actually what did I say? H minus 1 and so we are looking at RB H minus 1. let's keep that RBH to be height h, but where I'm using here, let's recalculate this h minus 1 by 2. So height as defined by length of path. So height h means that the path has h plus 1 nodes. So what should be the number of black? H by 2. So suppose you had height 1, then it means that you have 2 nodes. So one can be black, one can be red, right? So for height 1 you have h plus 1 by 2. It seems right. Yeah, seems right. Floor of this, yeah. And red, how many red? H by 2. Is it? I don't see that. Yeah, this is what happens if I change it in the middle. Yeah, so right now what I have done is just change this. So this path has length h plus 1 for height h, and we are wondering how many blacks and reds to give. So path has h plus 1 nodes. So equal would have been h plus 1 by 2 each. Yes, so how do we correct that here? So for red, we want to give more red, right? So let's make it h plus 2. And then we subtract this from h. So what do you get? H minus 2. Is this fine? So maybe this is also h plus 1. Yeah, okay. Yeah, so red we give h plus 1, halve it, and black we give just h plus 1 by 2, floor. So in some cases black will be less than red. Okay. Sorry? Black can't be. So what is the counter example for this? H equal to 4, you are getting 2 and 3. H minus 1. So then maybe, yeah, that was a mistake probably, okay. I see. So you are saying that red has to be, since red has to be less than black, there is no other option. Number of nodes in this case, well, height h, there are h plus 1 nodes. I am now doing the correct way. Yeah, I think let me save time and also notation. Let me just say both are equal. Let's just remove floor and ceiling, because it will not matter anyways for the idea. Let me just say that whatever nodes you have, you halve it. You should give equal to black and red, and so this height is what has to be now preserved. I'll correct it later in the notes in terms of exact floor and ceiling. So all paths to leaves should have black height h plus 1 by 2. Let me not put floor ceiling. So basically, in other words, think of h as odd. Then you will have exactly this case. So because of these two properties, that you want to minimize the number of nodes and that you have to preserve simultaneously every path from root to leaf to be of the same black height, it will make sense to use only black nodes everywhere else on the right part of this path. So this means okay, let me number this root as maybe x. So the right subtree of x is a complete binary tree of height equal to this that you want, h plus 1 by 2. Okay, so which now will give you the recurrence. So m, what were you using? M sub h. Yeah, m sub h is then equal to, so basically we'll write here the left size plus 1 for the root and the right size. Okay, so this is the only idea for the recurrence. So what is the left size? So in the left, what is the height? If you remove x, then the height falls by 1. So now the height becomes h. And is that a red black tree or not? The left subtree of x, is it arbitrary? How is that possible? It's a recursive structure. Every subtree has to be arbitrary. So the left, every subtree is an arbitrary. I mean, the axiom were actually recursive. So clearly, left subtree is also an arbitrary, but of height 1 less. Now height h minus 1. So for that, you should recursively pick RB h minus 1. So this will be the size of RB, so which is mh minus 1. Okay, so mh minus 1 plus 1. What is the size of the right subtree, which is the complete tree? Right. But I don't like this recurrence. Something is wrong in this. Say that again. The part what? Mm-hmm. So we should take the root node to be black also, you are saying. No, no, but will it be problem be solved if we say that the root is black? No, so I think it will be okay if we, since we want to fit the previous tree in this tree, yeah, I understand your point. So this also then we should try with the black. Let's try with black root, which means that the subtree that you are now looking on the right is also one less height. I mean the black height is one less. So this is h minus 1 by 2 now. And that's what I wanted here. Yeah, that should work. So, so this is a constructive proof. It will actually not only give you an estimate, but it will actually give you the tree as well. Okay, so I'm giving you a recursive construction for the minimum sized arbitrary. So its root is black, and this is how we'll recursively build it. So the recurrence for the size is this, and you can solve it. Black height would increase. Well, the height is h. There are h plus 1 nodes. How do you know? No. When I wrote this green hint, we did not use anything about the root or anything. There was no, this assumption was not being used. It was just an example. So the statement that you need is the longest path, which is which has h plus 1 nodes. How is the distribution in that path? It is not a statement about the root. It's only a statement about the distribution of red versus black in a path. But now this is an algorithm to actually build that tree. You can build it. It will satisfy this recurrence in particular, and this recurrence has solution. What is your guess? So you can check that its solution is the following. I mean, MH comes out to be at least this much. It will basically come out to be 2 raised to h by 2. You can check that. So MH, the minimum sized arbitrary, will have size of height h will have size at least 2 raised to h by 2. Okay, which will mean that the height is log. So this is the relation which we wanted. In the end, it is similar to the argument we gave for balanced BST or balanced tree even, but because of the red-black assumptions or axioms, we have to work much harder here. And there are these issues of floor and ceiling which I have to correct in the lecture notes later. But this is the proof. So now time is almost up. So this means that we have a good tree. Does it mean that it is balanced? Have we proved in this lemma that RB tree is a balanced tree? So this we have not proved, right? And we also don't want that for the algorithm. We don't care about balance. So this example is already this already should be unbalanced, right? You can see that first place is maybe the root. No, actually this is balanced. 4 and 3. Yeah, but you can build a RB tree which will be unbalanced, because in balanced condition we had this difference of 1 in the left and right height. That is very easy to violate in an RB tree. But as you can see, even being unbalanced, we can still show that the height is logarithmic. So this is what will be important in the time complexity. So yet RB tree could be unbalanced. Okay, so balance means that depth is log n, but if depth is log n, it doesn't really mean that the tree is balanced. It goes only in one direction. Okay, so we have to now do insertion. So insertion, you have seen how to do it in BST, but the big challenge now will be that in this red-black tree, when you insert, it will easily violate one of the axioms. Okay, because you will force to color that node also, either red or black. And if you color it inappropriately, then one of the axioms will be violated and you have to now do some transformations. So BST insert would violate one of the arbitrary axioms. So the correction will be either you recolor or you rotate. Okay, so recolor would mean that some nodes you may have to color red to black, black to red to preserve the axiom. And rotating a subtree, I have shown you one example. So you have a subtree, you can rotate it left or right once. So we'll show that insertion will be possible by just two rotations very locally. You insert by like the BST insert idea, and when there is a problem with one of the arbitrary axiom, you can rotate once or twice, and then it will be solved. Okay, so we'll do this tomorrow, and deletion will be more complicated. But deletion also will have only these two ideas.